Good afternoon, everybody. I hope everyone's having a wonderful day. So, anyways, just a couple things before we get started. um, the chat. I do think having the ability to teleport from one place to another sounds pretty darn awesome. It's going to be kind of like one of the things I'll talk about later on in this class. So it'll be pretty exciting. But anyways, so just a couple things. First, the assignment 1 is out. I recommend you start looking at it. You have most of the ideas to start it. You should be able to tackle the first few problems on there. So I recommend getting started as soon as you can, okay? Other than that, just keep an eye out, like just as usual. Like I put up my lectures every day along with the notes. I find generally, at least at this time, it seems like on Wednesdays they come out a little bit later because of just the way scheduling is on my end. But Mondays and Fridays I'll try to get a little earlier on for you. But the easy way you can tell quite quickly is if you keep an eye on that YouTube channel, or you just look at the course website on your courses, you can clearly see like, oh yeah, the course notes were updated, because I'll usually tell you when it has been updated. Like I'll just say last updated, and if it's like the current date or something of that nature, you know it's up to date. Okay. Anyways, I want to shift gears. I thought I would take a little break from talking about machines for a moment. I'll talk a little bit about languages. Then we'll come back to machines, I promise, because machines are sweet. So anyways, we're going to talk a little bit about what are called regular operators. Now, I want to give you some flavor for why regular languages are called regular. Now, you might ask, Dan, what does that even mean in the first place? Now, the easy answer I could give you, it was a name that was given to it by Stephen Cole Claney. The same guy I mentioned about the Claney star. That's the same logician that I'm referring to. He coined this term regular in like the 50s or something, around that time period. But that's generally where the word came from. But it refers primarily, at least when we talk about regular, we're talking about regular operators. So a lot of the things we're going to talk about when it comes to regular languages will refer and center tend to be around these regular operators at some point. It'll creep up to something later on we'll talk about called regular expressions. So I want to just define what regular operators are. We're going to do some examples, and then we're going to transition over to talking about something a little different, and then we'll talk about something really, really different. So anyways, the first of these operators I want to talk about, and this is probably the easiest one, because I almost guarantee you have some familiarity with this concept, is union. So imagine I give you two languages, A and B. I could denote union just like this, and it's no different than your typical definition of what union is for sets. So A union B is just X such that X is in A or X is in B. So just to keep it nice and simple, here's just an example. If I have A being this language that contains the strings dog and cat, and B containing muffin and cake, what A union B would be in this example is, what I do is I just lump all the elements in both sets together, excluding any multiplicities or duplicates. Why? Because we have unique elements in our sets. This isn't a multi-set, just to be clear. So I have dog, cat, muffin, and cake, right? Nice and easy. That's just your typical union, right? Are we all good with union? Union is basically, it's one of these set theoretic operations that, if you know a little bit about set theory, this is basically one of your best friends. Okay, that's union. Okay, the next one is concatenation. Now, we've seen what concatenation is earlier on, but I want to talk about it in a broader way. So before I told you about concatenation of strings. So I got to talk about concatenation of languages. So I have one language here and I have one language there, and I'm going to concatenate the two together. So if we know how to do it with strings, we know, okay, if I have two strings, what happens is I string A, string B, they come together, and I append one string to the other. When I have two languages, what I do is I take each string in one language and I append the other string in the other language to it. So I take each pair and I pair them by appending one onto the other. So let me just write this down. Now, concatenation, it's sometimes people like to write A with this hollow dot. Some also like to write just like this, just like when you do string concatenation. But you have to be careful because if, say, somebody doesn't know that A and B are languages, make sure you clearly define what A and B are if you're going to use this notation, because sometimes people will think, oh, you're talking about symbols, like A and B, like this. So it's usually a good idea to make sure you write down what you mean. So if A and B are languages, make sure you define A and B as languages. Is that clear to everybody? I just want to make sure, like, you understand, like, there's a flaw to using this notation if in case it's a little unclear to your reader. Sometimes people use this one, but I don't care which one you use. I tend to prefer this one. But all it is just it's just concatenation of strings such that X is in A and Y is in B. So all we do is just take each string in A, and then you take and append each string in B. So let me just do an example. So if I have AB, like I have with these two languages here, all I do is I take dog muffin. So now I have dog muffin. I don't know if I should be pleased or not. And I also have dog cake. So notice I'm just looking at dog and then I append muffin and then I also append cake to get two separate strings like this. And now I have to do it with cat. So I take cat. So I take cat and I have a cat muffin. You didn't think you were going to hear about cat muffins today, did you? A cat muffin and a cat cake. Listen, when I hear cat cake, I just think of some picture of a cat with like a cute little birthday cake with a little hat on. That's sort of what I imagine when I hear cat cake like this. But it doesn't have to be. I just thought it was fun. Okay, so that's number 2. This is the last one. This is the one that, now we've also seen a shade of this one before as well. It's star. So sometimes people call this closure, or they call it Kleene, closure, or star. Kleene, closure, or star. You'll notice that before I also mentioned about Kleene star before. This is, so cat shaped cake. That's a good one too. So these are just different names for the same thing. Just whenever it is unclear, you just write it out, okay? I'm just going to call it star because it's easier just for me to say star. If I say closure, just think star, okay? Hopefully I'm clear. So let me define what star is for a language. I'll define it and then I'll give you some intuition with it and we'll do an example. So if I give you a star, now this isn't the algorithm a star, this is a language applied to the star operator. I'm going to have it so it's x1, x2, x3, all the way to xk, where k is greater or equal to 0. And each xi is in A. Now, earlier on in the term, when I talked about sigma star, so you may recall sigma star, I'm talking about the same idea, but the difference here now is I'm talking about strings, not symbols. So when we did sigma star, you remember it was just all the possible strings you could form using those symbols, really just of your alphabet, right? Here we're just going to take that idea and instead of just being one symbol, it's going to be a string in your language. So just to give you a little bit of intuition, so you're going to have every single possible k involved in this. So if, for example, you fix k, you would have the example we talked about maybe towards the beginning of this class, where we had it where, okay, you can have like a raised to the k. But let me give you some idea of what this means, because this looks a little intimidating at first. So let me just break it down. So I'm going to say that is adopting the power notation to instead strings, with our example. So I'm just going to do it with the example in mind. Actually, it's okay if I do it on the next board here. Just I think it's a little bit easier to see. Okay, let's migrate over here. Okay, so I'm just going to use that notation that I used when I was talking about sigma. So remember I had sigma raised to the 0. I had sigma raised to the 1, sigma raised to the 2, and so on. I'm going to use that same idea here, except instead of symbols, it's strings. Okay? So instead of thinking about I pluck off one symbol from the alphabet, it goes into the string, you got to think of it as I have one string, I throw it into this other string. Okay? It's going to be a little bit more meta on top of it. So here's a way I find a little bit easier to follow this. Okay. So if I give you a to the 0, I'm talking about all possible strings of that language such that there are 0 of them. But there's only one possible set of these. It is, what would be in here? If I have 0 strings, there's a special string. It's the empty string. So it's the empty string. Perfect. So now if I union this with a 1 like this, I'm going to pluck off one string from A. I'm going to have one of each. But what's A? A consists of 2 strings, dog and cat. So what's A to the 1 then? It's, let's see, dog and cat, right? It's one string of each. So remember, I'm only allowed, when I have A to the 1, I'm going to think about, okay, I'm going to think about all possible strings I could form using elements of my language. So if it's A to the 1, you can think of it as, okay, well, there's 2 possible strings, dog or cat, right? That's only one of these. So naturally, if you think about it as, okay, if I have A squared like this, now what you got to think about is instead of it just being dog and cat, now you have to think about it like you have now 2 strings concatenated to one another, but they can be elements from the language. So, for example, I'll get us started. So I have dog, dog. So, for example, that's an element, dog, dog. Can somebody else give me another element? Dog, I heard dog, cat. That's a good one. Somebody give me another one. A cat, cat. Very good. And there's one more. Yeah, we have cat, dog. Perfect. So that would be what's in here. And this goes on forever, okay? So just to write this out, so just with my example, if I write down A star, I'll just kind of lump all these together here. So I have epsilon, dog, cat, dog, 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 cat, cat, dog. That sort of melted there. Cat, 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 cat. And now if I want to consider strings, sorry, I want to consider A to the power of 3, then I have to take 3 strings from my language, and I'm going to concatenate all possibilities of them. So now you'll notice that this one's going to be a little bit bigger. So I have dog, 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 cat, dog, cat, 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 cat. You can feel the pain in the way I'm writing this. Cat, cat, cat. Let's see. We got, I think, cat, cat, dog. Cat, cat, dog. And I think there's dog. Dog, cat, dog. Dog, cat, dog. And then I got cat, cat, dog, cat. let's see, 1, 2, 3, 4, 5, 6, 7. Did I miss one? Let's see here. Does anybody see one I'm missing here? So I have dog, 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 cat. Cat, dog, dog. Let's see, cat. Yeah, it looks like that. Yeah, perfect. Thank you. Yeah, because we should expect 8. We should expect 8 for the length 3. Because we have 2 symbols. Sorry, not 2 symbols. We have 2 strings. We have 2 strings. And we can concatenate up to 3 of them, right? So it means I could pick one or the other, but I do this 3 times. So you would expect it to be 2 to the power of 3. So that's an easy way you can know how many there should be here. So how is the star operator? Is this clear to everybody? So instead of thinking about it like we had with sigma star, where you have one symbol and you just say, okay, well, what all the symbols, like if how many strings can I make with, say, 2 symbols or so on. Instead of thinking of each, so all I've done is switch the type on you. Instead of it being just a symbol, now it's a whole string. So just think of dogs and cats, okay? Are we all good with this? I just want to make sure. Okay, I think we're good. Now, I want to give you a very important property that I want you to be aware of. All regular languages are closed under regular operators. Regular operators. To be more precise, or more exact, that is, if L1 and L2 are regular, then the following is true. So now this is where, if you're not sure what the word closed means in this sense, all I'm going to tell you is, okay, so if I have L1 and L2, if I perform any one of these operations, the language remains regular. So what I'm saying is, if you have L1 union L2, that's regular. If I take L1 and I concatenate it with L2, it's also regular. If I take L1 and I apply the star operator, it's also regular. Bam! Isn't that neat? So if you do any one of these operations, you get regular language for free, okay? So if you show me, for example, that L1 and L2 are regular, that means up to our point, we know that if it has a deterministic finite automaton, then we know it's regular, right? So if I know that one language that I could design for a DFA is regular, and I get another one, I can, if I want to look at their languages, if I take any one of these operators, I know it's still regular. That means that there still exists another DFA that has actually recognized that language. Is that clear to everybody? So it's going to be kind of, so at first this looks a little bit more abstract, but I assure you, as we build more machines, this will become more concrete for us, okay? Because once we see, because remember, like I said, when we defined what a regular language is, we said, okay, it's just as long as there's a DFA, right? But you'll notice that I didn't really describe DFAs to you here at all, right? I'm going to give you the machinery to do that at some point here, okay? Is that clear, everybody? So I'm not going to get there quite yet, but we're going to get there eventually, where I'm going to be able to show you ways to transform. I don't want to spoil it too much, but we're going to get there, okay? Okay, so I think we're good for that. Now, that's the first thing I wanted to show you. So this is actually the most normal thing about today that I've got to show you. And we're going to be talking about cat muffins, okay? So the next thing I want to do is I want to revisit something. Whoop, we lost the penguin. The next thing I want to revisit is, remember the other day, I had defined for you the language of a machine. So I gave you kind of this informal view of what that means. I want to give you now a formal way you can process all the strings. And this comes back to delta, the transition function. I told you we would come back with a vengeance, okay? So it's back. So I want to define, so we're going to talk about a formal definition. So I'm going to give you a formal definition of computing for DFA. So I'm going to define something. And at first, this is going to look a little strange if you're not familiar with me defining things inductively or recursively. So don't worry, I will be doing a good example with it. If it looks a little alien at first, don't worry. So recall, DFA M defines a language L of M. Remember, we did this the other day where we defined that L of M is the language that the machine M would recognize. I'm going to define this formally now. And also how we process strings with a DFA. Now, we're going to define it formally. We can define this more formally. So the whole idea here is that, remember when we process the string, I told you, okay, read it from left to right, and you read each symbol, you read off the transition, and you go to the next state that it tells you from the transition function. I'm going to give you a way you can mechanistically determine that. We're using an exact formula, but this formula is going to be defined inductively. So that's how we're going to do this. So we can ask for formally by extending from symbols to strings our transition function. So you know our transition function, it takes in a state, a symbol, and it gives us back a state, right? So I'm going to now create a generalized version of it that takes in a state, a string, and then it returns me a state. So the whole idea is that this extended transition function is going to be able to chug through my string so I can actually compute the state at the end. Over our transition function. This is the extended transition function. And I'm going to define it as delta hat. That's just a hat symbol, it's a little caret. It's going to take in a state. It's going to take in a string. So remember, this is a state. This is a string. And it's going to return to me a state. Which we define inductively as follows. Now, if you don't like my induction definition, you can always rewrite it recursively. So everything I'm going to describe here, there's two ways of interpreting it. You can process the symbols one at a time, inductively building up to the entire string, or you can take in the entire string and recursively dissect it top bottom. So I just want to make sure you have an idea of this. So let me write this down. So first, I'm going to define the extended transition function for the empty string. So when I define things inductively, I'm going to define a base step. I'm going to call it the basis. So you can think of this as your base case if you're thinking recursively. So basis is going to be that delta hat, or the extended transition function, given a state q and the empty string, it gives me back q. Now, at first, you might look at this and say, Dan, what the heck is that? What I'm saying is, given Given the empty string, our extended transition function just spits me back out the state because it didn't go anywhere, right? So the whole idea is that you got to imagine the extended transition function like if I gave it a string and it feeds through it. If I give it the empty string, nothing should happen, right? It should just stay in the exact same state I began with. Does everybody understand that? So that's the intuition why this is going to be first initially defined given the empty string, so that I can build on top of this. So just to be clear, this says no symbol has been read. So the DFA is still in state Q. So if I give you a state Q and the empty string, it better stay in state Q, right? So that's the base case or basis. Now here's the induction. You can think of this as the recursive case if you prefer thinking about it this way. In fact, I encourage you to do that. So if a string W equals XA, where A is a symbol and X is W less the last symbol, then, so all I'm doing is I'm just plucking off so I'm writing this so that this is just the string W less this last symbol. So I'm just plucking off the last symbol and writing it out separately. Is that clear, everybody? So all I'm going to do is here's how I'm going to define it. So I'm going to have delta hat of QW is equal to the transition function delta, given its first input is going to be delta hat of Q and X, and its second parameter for the transition function is going to be A. So do you see what I've done here? I've dissected the string. I've essentially isolated out the last symbol. So do you see how I can build up and determine a state using this definition? If you don't see it quite yet, we're going to do a full example, so don't worry. But the first thing that should stare right you in the face is that this looks like recursion right here. This is recursively defined. That's the first thing that should sit out at you. It's like, okay, well, like what the heck? How do you calculate this? well, you just apply this again, right? You just say, okay, well, now X is just it less its last symbol, and you evoke it again. And you can keep recursively working your way down until you have the empty string. So this is where that recursion, that fun of recursion starts kicking in, okay? So has everybody got the definition down? Because we're going to do a full example, so that way everybody's got the idea. Because each one of the machines that we're going to see is going to have well, essentially, I'm going to start off by defining these extended transition functions for the machines that we're going to look at, because then you'll have an exact way of defining all of the strings that are accepted by your machine. And because it's defined inductively, we can take advantage of that fact to show that the machine does exactly what you want it to do. So are we all good with this? Is it okay if I erase up here? I want to keep these two down here because it makes it a little bit easier to walk us through this example. Are we all good with that? Okay. So just remember the extended transition function delta hat. It takes in a state, it takes in a string, and it's going to spit out a state. So I'm going to start off by just kind of making us have a little bit of fun here. So first, we're going to design a DFA, and then we're going to try simulating a couple strings on it using this extended transition function. So let's try to design, let's make a DFA that accepts binary strings with exactly 3 ones. Now, the last day, I showed you how to do it where you can get at most, right? So I'm going to start off by just starting off with that kind of picture, and then guys are going to tell me how I can change it from being to at most to exactly 3. So I'll start off drawing a transition diagram for us. So I'll indicate a start state. So I'm going to start off on Q0. I'm going to, actually, let me draw the chain out like we had before. Q1, Q2, and Q3. I think I have Q3. And Q3 I had as a final state, right? In the previous example. Like when we did this, when we had at most 3 ones or 3 zeros. I can't remember if it was ones or zeros. Regardless, the idea is going to still apply. 0, and then I had a 1. Now, this is where things are going to get a little bit different. I want to ask you guys, because I think it's very important that you see this. So before I had at most 3 ones, right? So before I had it so that I used this path to get me to the final state, and then I just allowed it to take any more ones and zeros, right? But if I wanted to have exactly 3 ones, what can I do to this DFA? Like, keep in mind, what we had before was that it says 0, 1 right here. What can I do to modify this DFA? Okay, I see a very good one in the chat here. So what we're going to do, this is actually the perfect suggestion, is it says, so we have a lovely suggestion. It says you add one more state, I get stuck at if you add this one as a fail, right? Yeah, that's the idea. We're going to create what some people lovingly call a fail or garbage state. This is where Oscar the Grouch hangs out. So I'm going to create another state. I'll call it Q4. I'm going to change this so that I can't take any more ones here because I want it to be exactly 3 ones. So I'm just going to allow it to only be zeros here because I want to make sure it only can take exactly 3 ones. I'm just going to push it over here. So if a 4th one pops up, I send it to this garbage state over here where it could take in any number of zeros and ones. So some people call this like a garbage state. So that's one way you could get around. You could change an at most to an equals if you ever find yourself in that predicament. Is you introduce one of these garbage states. Is that clear to everybody? So like all we did was just took the idea we had before. We just added this little tweak to it by invoking this idea where if we had a little bit of extra stuff, we just want to make sure it gets shoved somewhere else. So this is like, so some people call this a garbage state or a dead state or a fail state. Usually a dead state is usually one where it like everything goes to it. This one is just like if there's something extra like extra carriage on a string, you just kind of just throw it over there. That's kind of the idea. So I think everybody should be fine with this one. Is everybody good with this? I think we're good. Just don't be shy. Okay, so now I'm going to process some strings on this. So let's start off with something like, so let's do an example. So consider W being all ones. Then, so I'm going to feed all these ones to the extended transition function. To do this, I'm going to build it bottom up. Now, like I said, you could recursively do this top to bottom. And in fact, I encourage you in your spare time to try this. The only reason why I'm not doing that is because you write out a lot of parentheses and it's like bookkeeping parentheses, okay? That's why. But you should try it once, okay? So what I'm going to do is I'm going to just start building up from this base step or basis. Now, first, when you look at this all 4 ones like this, you know right away this thing better get rejected by this machine, right? Because it should only accept 3 ones. So that should be what we should anticipate here. So I'm going to start off with my extend transition, delta hat, Q0 and epsilon. That spits out Q0 because Q0 is the start state. So far, are we doing good? So I'm just literally just writing this out. Now what I'm going to do is I'm going to feed in the first symbol So delta hat Q0 given 1. Now I'm just going to invoke the induction part of this definition. So all I do is I look at 1 there. What's 1? 1 is, you can think of it like I rip off the last symbol and then there's everything else that's sticking around. What's everything else? It's empty string, right? So that is just the transition of delta hat Q0 epsilon, comma 1 like this. Because remember, W, if you look at W and I look at it as 1 right there, you can write it as empty string 1. Does everybody see that? That's very important. Are we all good with that? I just want to make sure. Perfect. So now the great thing is we already calculated this. This right here is Q0. That's Q0. So it's Q0 given 1. Where do we go? We follow our finger. We look at the labels. So I have Q0. I read off a 1 and I get Q1, right? So I'll just rewrite this as Q0, 1 like this. I'm just writing this what I have right here, which we know is Q1. So now I'm just going to keep proceeding this way. So I'm just going to write it up here next. So delta hat of Q0, 1, 1. This is delta of delta hat Q0. So remember, this is string W. This is X. That's A. So now all I'm going to do is I write down Q0, 1, comma 1. So what's this? What's that? That is Q1, right? That's Q1. So I got Q1, 1. So this is delta Q1, 1, which should take us to Q2, right? If we just follow our fingers on that label, it says Q2. And then if we do this again, delta hat Q0, 1, 1, 1. This should be delta of delta hat Q0, 1, 1, comma 1 like this. Which, of course, this we already computed. That's Q2. Q2, 1, which, if you look, I read the 1. I should be better going to... Now, keep in mind, remember, this is still formally defined. I'm just using the transition diagram to make this easier. And that takes me to Q3. And naturally, when it's okay if I delete I'm getting a little ahead of myself. It's okay if I delete this definition here. Because I think we got generally the gist of this, right? So remember, all I'm doing is I pull off the last symbol. And I'm just building up it inductively. So the last one here, so if I have delta hat Q0, 1, 1, 1, 1, so I have 4 1s. This is delta of delta hat, I was getting a little excited there, delta hat of Q0, remember, it's these 3, 1, 1, 1. The last one's A. But we already computed this. This is Q3. That's Q3 right here. I read off a 1. That better take me to Q4, right? So it's Q3, 1, which is just Q4. Now notice that this is not a final state, right? That's not a final state. This is not in F. So we reject. Does everybody see how we could use this extended transition function to compute and process strings for our DFA? So notice it's just a more formal way of just doing what we were doing before, except now I actually have written it out exactly for you. So it's not following fingers or I feed one into the other. I've formally defined this. I feed the transition function to the next symbol and then I process it. That's literally what this is. So are there any questions about this? I just want to make sure. In the notes, I give another string where it should be getting to an accept state. So I'll let you take a look at that later, just because I want to get to another thing here. But now I have a question for you. Given this definition of an extended transition function, I want to define the language of a DFA formally for you. Let me define a language of a DFA. So let me first write out the first part here, and then I'm going to get you to help me with this. Formally, the language denoted L of M of a DFA M is, so if I write out L of M like this, and I tell you, okay, it's supposed to be the set of strings such that, what should I write over on the right side of this such that? Does anybody have any ideas? So remember, notice how this, when I compute the extended transition function on my string, it will tell me a state at the end, right? In this case, it rejected it. But there's going to be some of these strings that get accepted, right? So what should go right here if I want to define the language of my machine M? Does anybody see it? So I'll start writing. If I hear anything, I'll turn around. So it's going to be delta hat. What should I write first here? So it's going to involve the extended transition function. What should be the first parameter of the extended transition function? Well, it better be, yeah, Q0. Q0, yeah, it's the starting state, exactly. So Q0. What should be the next one here? Well, think about it. W better be in that language if it gets accepted by the DFA, right? So what should go right here? It should be that input string, right? W. It should be W. Such that W is what? What is this extended transition function? What state should it spit out at me? It should be a final state. So remember, it outputs a state. So as long as it's in F, the set of final or accepting states. So here's our formal definition of a language of a DFA. We defined it formally, and that's the one we could use for a DFA. Perfect. But yeah, no, in our case, like say if we're looking at this example, F would of course be the set containing Q3. Perfect. Perfect. Wonderful. Are we all good with this? Because I want to talk about one more thing today, and this is the one I told you it was going to be a little bit strange today, and this is the strange thing I want to talk about today. Are we all good? Don't be shy. Because I'm going to shift gears from DFAs. We're going to talk about so-called non-determinism. So let's talk about this different concept. Now, I alluded to this earlier on in the class when I started talking about finite state automata, that there's this concept of non-determinism. Now, in a deterministic finite automata, or DFA, we had it so that every time we process a string, when we go from one state to another, it's always that there is one state to go to another state, right? So I want to give you this idea of non-determinism. Let's not add this. Let's go. Non-determinism. So non-determinism. Now, how many of you have ever heard of non-determinism before? Some of you may have, some may not have. Now, if you've taken something like CS340, you may have heard of this before. I'm going to be defining it in a different way that involves machines. So you may have heard of it like as something involving accepting or something of that nature. You may have heard of some other things. I'm going to I want to give you a couple of intuitions about non-determinism, okay? So first, I want to contrast this with a DFA. So in a DFA, when given a state, and an input symbol, the next state can and will be determined. It's deterministic. So that's what makes a DFA, is that I go every single time I process one symbol, it takes me from one state to another state. There's exactly one state I transition to. So we're going to be now considering non-deterministic machines. Now, let us consider non-deterministic machines where several states may be selected for the next state. When processing a string. So the big thing I really want you to take from this, other than the fact that it's now we're talking about that the machine could be in several states at the same time, as opposed to just one state. The big thing I want to point out is that non-determinism generalizes determinism. So you got to look at deterministic as a special case of non-deterministic. You'll see why as we proceed in this course. So every DFA is a non-deterministic finite automaton and is an NFA. So I briefly mentioned about what an NFA was. It was non-deterministic finite automaton. That I'm just basically saying you get basically an NFA for free if you have a DFA. So I have enough time. I have a couple minutes to motivate non-determinism, and then next time we'll come back, we'll define what an NFA is, and we'll see some examples. So I want to give you a couple of intuitions of what I mean by that the machine can be in several states at the same time. So I want to give you a couple motivations behind this. So the first one is this one that some people like to call guessing. I like to call it perfect guessing. This is the one you may or may not have seen in something like CS340. You may or may not have. It's okay. We're going to talk about all of it and rip it open with all its juicy. I'm getting so excited. All the juiciness of this idea. So the idea is quite interesting and quite magical in some ways. The machine is able to guess choices that lead to a final state. If there is at least one selection of guesses. I'll define what these guesses are more exactly next time. Next selection of guesses that leads to the machine being in an accepting state. the machine guesses it. So that's the first intuition. Is it okay if I borrow 2 more minutes from you? Is that okay? So I have one more intuition I want to get to you. I want to elaborate on this because this seems a little strange. Is that okay with everybody? Just want to make sure. I don't see any problem. So let me proceed. So this machine, you got to imagine it like I could splay out whenever I have a choice to make between one state or another state. What this machine is capable of doing is so-called guessing, but this guessing is not just, oh, I flip a coin and I pick one. It's even more powerful than that. And you can even view this also towards the coin flips too, but that's beyond this class. But the idea is that if, say you have a choice between more than one state you could go into with your machine. Remember, in our DFAs, you go from one state to another. It's deterministic. In ours, we're going to have a set of states that you could go towards. So you're going to have a set of states. What you could do with this machine is you could actually go through and you could imagine this being able to move itself through performing guesses of which state to go towards, but it will know which one it could go to get into an accepting state. Which, on the face of it, should sound a little strange to you because I want to ask you guys, what kind of power would you need to do that? It's like, what kind of power would you need to do that? Like we talked about teleporting. Yeah, you need to know the future. You need clairvoyance. You would need to know how you could get through all those guesses to get to the end, right? You would need knowledge from the future. And that seems like something that a machine that we would have would not have that, right? That seems like magic. At least as far as our ideas of what a machine is, right? But that's basically it. Like I said, I was promising you some superpower that was like teleporting. We got pure clairvoyance here where I can have the machine go through any set of guesses, and as long as it gets me to an accepting state, the machine is capable of doing that. Now you might ask, how does it reject? It rejects when all possible accepting states would never be possible to do. So when it performs and gets if it rejects, there was no way to guess correctly. So it would just give you any wrong answer. Which is strange. Like it's some voodoo stuff here, okay? But that's one intuition. I want to give you one quick one. This one's way more intuitive than this one. I want you to just think about this for next time, okay? But the second one is massive parallel threads. So I'll let you take a look at it in the notes, but I'll just explain it in words here for you, and we'll see it in the example next time, what I mean by this. So another intuition is this idea that you can view the NFA, or this non-determinism, like a parallel machine where if there's ever a possibility that you could branch on one of two possible states, you spawn threads for each transition from one state to the other. So instead of having it where you think about this this superpower where I'm able to tell you, like I'm able to know where the accepting state is without knowing that information, but somehow I have that magical power. Instead here, what I have is if I can go to a set of states, I can go to those sets of states, but it requires me to spawn a parallel thread like I'm operating on a parallel computer or a parallel architecture. Now, the thing that's not very realistic about this idea, but it is something more realistic, right? Is that every time you perform a branch, you're going to spawn another thread. So for any arbitrary input, you're going to have many, many, many threads, so many that you may have a hard time following all of them. Is that clear to everybody? So is this idea kind of clear? So instead of having, or I imagine I have this pathway of guesses that I could pick through states, instead what I'm going to have is that I just have the ability to go through all of them by spawning parallel threads that execute all at the same time. So you can think of it like it's not just perfect guessing, it's literally that I could branch all of them. And whenever I don't find a transition, I kill that thread or that thread ends. Because in our NFAs, we're going to have it so that we can transition on, we can have it so that transitions don't exist for symbols, which is going to be another thing that's a little different. So that being said, when we come back, so I want you to think about these two. Just take a look in the notes. I have a little bit more detail about this. But when we come back, we'll define what an NFA is, and we'll see some examples of this, especially this second idea. And I'll try to kind of connect these two together with this. So if at first this looks like some hocus pocus stuff here, don't worry. We'll see more of this stuff next time, okay? So I say thank you very much, and have yourself a beautiful day. I'll see you later. Oh, we have... Okay, good, good, excellent. That's exactly, this is the kind of stuff you have to think about. It will pop up. I'm just going to stop recording.